Hey guys, how's it going? Is
Hello.
that
Hey
Aubrey?
guys. No, this is Blake.
Oh,
I
no,
think
no.
Aubrey's.
Yeah, it's just Aubrey's in here tonight.
I am. Hello.
Hi, glad to have you here. I can't figure out. Oh, that's why. All right. Okay, guys, test is on Tuesday. Test is on Tuesday. It's going to cover everything up to periodic trends. So we're going to do chapter 8, 9 up to periodic trends and thermochemistry. The bulk of the math is going to be the thermochemistry. Okay? We good on that? Are we good?
Yep.
Okay. Good enough, guys. Did you get my emails about the quiz? I blew 2 answers on the quiz. One, I put the right answer was in there, so I graded it just as I graded it. If you got the right answer, you got the points. If you didn't, you didn't. The other question, I didn't put the right answer in there, so as a consequence, everybody got credit for it. Good enough? I'm getting crickets here, guys. Good?
Yeah.
All
yeah,
right.
good.
All right, I've got 3 of you in here. All right. It seems like everybody's, 4, there comes Dylan. So what I'm going to do right now is I'm just going to go through and review the quantum numbers that we discussed on Tuesday, okay? The principal quantum number, it can be any number, any integer from 1, 2, 3, 4, 5, 6, or 7. Those are the choices. Yeah, it can have 8, 9, 10, 11, but realistically, the periodic table doesn't go that far. So the principal quantum number can be up to 7. And what it does is it tells you the size of the orbital. Now, the second quantum number, the L, that gives you what's called the angular momentum. What that does is that dictates the shape of the probability graph. So if L can be any number from n minus 1 down to 0. So if n is 3, L cannot be 3. If n is 3, L can be 2, 1, or 0. And you also have to understand with L, 0 means we're dealing with the s orbital, 1 with the p, 2 with the d, 3 with the f. So the L deals with the orbital shape. The M sub L deals with orientation. Like, for example, if I'm dealing, it doesn't matter with the S because there's only one suborbital. But if I'm dealing with the P, that P orbital can be located along the x-axis, along the y-axis, or along the z-axis. So it depends upon the suborbital you're putting it in, what the value of M sub L can be. And M sub L can have values minus L, integer down to 0, integer up to plus L. So if L is equal to 1, M sub L can have values of minus 1, 0, and 1. If L is 2, M sub L can be minus 2, minus 1, 0, plus 1, plus 2. So the M sub L is going to dictate which orbital it's in. Now, the fact that L is 2 means that I have got 5 suborbitals in that d orbital because it can be minus 2, minus 1, 0, plus 1, plus 2, 5 orbitals. And each orbital can hold 2 electrons in it. The last one is called the M sub s. And basically the M sub s just directs the electron spin. It can be either going in a clockwise motion Clockwise or counterclockwise motion? Are we pretty solid on the quantum numbers, guys? Dylan, give me an amen.
Amen.
Thank you so much. Now, Pauli's exclusion principle says no two electrons can have exactly the same energy. Now, when we're dealing with quantum numbers, those were a solution for the energy. So in effect, what this is saying is no two electrons can have the same exact quantum numbers, which is why the M sub s was introduced. The M sub s will dictate different energy levels depending upon if the spin is going with the magnetic field or against it. Because anytime you have a charge that is spinning, you create a magnetic field. You can have it go with the magnetic field or against it. And depending upon whether it's with it or against it, you can have a positive or a negative effect on the energy for that particular electron. Are we good with this? Are we pretty solid on this stuff so far?
Yeah.
Oh, one more thing, guys. Make sure you know I went over the development of the quantum mechanics. There will be one essay question on that on the test on Tuesday. Any questions on the orbitals, on the quantum numbers, or the development of the theory? Wave numbers, Rydberg equation, anything. The only numbers you're going to have to crunch in the quantum mechanic field are going to be taking wavelength through to frequency, through to energy, and back and forth. Or you may have to use, or you probably will have to use Rydberg's equation if an electron goes from one energy level to another, figuring out what the change in energy is, and then using that to go back to seeing what the wavelength of light is. Questions, guys? I'm getting a whole lot of crickets out here tonight. Is that because you're not understanding this stuff, or is that because you really want me to continue on?
I'm good.
Thank you, Blake. Okay, so we're going to get into chapter 9, and we're going to get into a lot of stuff you had before. A lot of the stuff we're going to deal with right now is going to be stuff that you had in intro. Where am I going with this? There I'm going with it. Okay. Can you see the screen? PowerPoint?
Yeah.
Good enough. Okay, a lot of this stuff you've had before. We're going to deal with electron configurations. We're going to deal with the orbital diagrams tonight. We're going to deal with assigning quantum numbers. And once those numbers, if we have a set of quantum numbers, we're going to be able to say which elements last electron matches those quantum numbers. We may get to effective nuclear charge. I don't believe we will get that far, and we may get to periodic trends. So we can use the periodic table to tell us which electron, which L number we're dealing with, depending upon the area of the periodic table we're dealing with. Just remember, the N value is the shell value. If you go down the rows of the periodic table, every time you go down a row, you increase the value of n. If you look at a periodic table, and I'll pull one up in a second, the first two columns, the two columns on the far left, are where the s orbitals are filled. If you look all the way to the right, the last 6 on the right side of the periodic table are where the p orbitals are filled. Those are groups 13 through 18. If you look in the center where the periodic table dips down, those transition metals are where you're going to find the Ds. And the Fs, the lanthanides and the actinides, are where the f orbital gets filled. Remember, if I've got an L equals 0, I have an s orbital. L equal 1, a p. L equal 2, a d. L equal 3, I've got an f. And really and truly, guys, if I'm looking at the way the periodic table should be drawn, I would have the F's right after the S's, F's right after the S's, and then after the F's, the D's. And this is the way they get filled. 1s is hydrogen and helium. This n equal 2, we can fill up 2s, 2p. N equal 3, 3s, 3p. Then we come into a little bit of a situation. The 4s electrons fill before the 3d. Now, the 4s orbital and the 3d orbital are very, very, very close in energy to one another. The difference is D has 10 electrons in it. S only has 2. So the fact that there are 10 electrons in the Ds makes that more energetically unstable. It has a higher energy than the 4s. So the 4s gets filled first, then the 3d gets filled. 4p, then we go back to 5s. Same thing. 5s, 4d, 10 electrons, gives the 4d just a tad more energy than the 5s. We fill up the 4p, we go to 6s. Now we have 14 electrons. That has made the F electrons in the 4th shell have more energy than the s electrons in the 6th shell. Bottom line, do you have to memorize this? No, because you're going to do a chart. If you draw this chart out where you put 1s on the bottom, next row up 2s, 2p, next row up 3s, 3p, 3d, next row up 4s, 4p, 4d, 4f, 5s, 5p, 6d, 5f, 6f, 6p, 6d, 6f. If you just fill it out in this fashion, then what you're going to do is you're going to take the feather end of the arrow to the head, and you're going to go make parallel arrow marks all the way up here in this chart, so that we go from the tail to the head of the arrow. We fill 1s first. Then we go from the head back to the tail. 2s gets filled. Head back to the tail, 2p, 3s. Head back to the tail, 3p, 4s. To the tail, 3d, 4p, 5s. This is just a great way for you don't even have to memorize which ones you fill first or which ones get filled next. Great chart to help you do that. I take it you've been shown this before. Am I correct?
Yeah.
Okay. Won't go any more on that. Okay. we're going to deal with electron configurations and orbital diagrams. Electron configurations are what you already know. These are the numbers that have a 1 in front of a letter and a superscript after it. The 1 stands for the principal quantum number, the shell that those electrons are in. The S stands for the angular momentum. S gets translated to an L value of 0. And the superscript up on top stands for the number of electrons in that orbital or subshell. Okay? I'll get into orbital diagrams a little bit later, but we're going to start with electron configurations. So if I have an H atom, I have to start at my lowest energy level, and I have 1 electron in that lowest energy level. So I start with 1s superscript 1. If I'm dealing with an orbital diagram to represent this, I'm going to draw either a line or a box. I don't care which one you like to use. But please do this for me when you are writing the energy levels. Please do not go from left to right. Please go from the bottom to the top, because that's showing more and more energy if you write it from the bottom to the top. Will I accept it if you write it left to right? Yes, I will accept it. But I don't like it as well. It's harder for me to grade. So if I have 1s, I'm going to draw the orbital as a box. And in that orbital, I am going to put, I'm going to put an arrow going up to indicate that the electron is spinning in one direction. All right, when we're dealing with the electron configurations, we deal with the number, which is the shell, the P, which designates what the L value is, and the number of electrons that go in there. Periodic table. If I have cobalt, cobalt is down here at number 27. All right. If I'm going to do the electron configuration of this, remember, I've already drawn my nice little chart with my 1s, 2s, 3s, that little chart with the arrows going up. If I'm going to figure out where my cobalt is, I have 27 electrons I have to account for. My 1s is going to be filled with 2 electrons. This is going to designate my 2s. I can put 2 electrons in there. So now I've used up 4. I've got 1s, 2s. Move over to my 2p's. I can put 6 into my p's because I have 3 suborbitals in my p orbital. Each orbital can hold 2 electrons. So I then go to p6. I've used up 10 of my 27 electrons. I go to the next level down, which is going to be 3s. I can put 2 there. 12 gone. I go over to my 3p. 6 in there. That means 18 are gone. Now I come to my first anomaly. The 4s gets filled before the 3d. So I have to put 2 electrons in my 4s and 1, 2, 3, 4, 5, 6, 7 in my 3d. So if I write that all out, I've got my electron configuration of cobalt. Any questions, ladies and gentlemen? Okay. Joe, you have 10. Joseph?
Yeah, what's up?
Okay, you have 10.
Oh,
I got to
goodness.
move this silly thing. 10's down here. What is the electron configuration of 10?
First, it's 1s2.
1s2?
Yeah. And you go to the next level, which is 2s2.
Okay.
And then, I mean, it's going to be like pretty much 2p6
Go for it.
and 3s2
Mm-hmm.
and 3p6.
Yep.
Then 2s2 again. No, 4s2.
4s2, good.
Then what's that next one? 4p,
Nope.
4d,
Nope.
f.
Nope.
Suck.
Guys, if you haven't done this yet, fill it out. Okay, Joe. You're up to the 4s2. What's the
Okay,
next
it's
orbital that fills?
3d, 3d,
Okay.
3d6. No,
Nope.
1, 2, 3.
No.
4.
How many orbitals are in D?
10.
10. Or how many electrons are in D? 10. 5 orbitals, 10 electrons.
It's 3d10.
3d10. And I'm sorry, I'm trying to get back to where there we are. So this is where you're at. You're at zinc, 3d10. What's next?
3p10. No,
Nope.
3p6.
Nope.
3.
Nope.
Is it 3p?
Nope. You did the 3p. The 3p's were in AL.
Oh, 4p. 4p.
Right. 4p
4p6.
what? 4p6.
And
Keep on going.
4d10.
Nope. What goes
I'm looking.
between the... I'm telling you, Joe.
I have it. It's 4s then?
No, yeah, not 4s.
5s.
5s.
Okay, 5s.
What?
2.
How many? 2. So 5s. Then you go back down to
4d. Okay, I'm looking at it wrong. Yeah. 4d10.
All right.
And
Now we're at
5
the point. We're at the point. All right. So we're down at cadmium now. So what is the next orbital?
Next one then is 5p6.
Nope. Sorry, I keep on saying that harsh. Nope. Sorry about that. Where do we got to go, Joe?
I hope. I think I. Okay, 5d.
No. You were right with the 5p. You're right here. You're at
5p6.
cadmium. But how far you got to go over, Joe?
Oh, 10. Okay, so 5p2 then.
5p2. So if I'm doing that in retrospect, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then 5p2. Questions, ladies and gentlemen?
Nope.
All right, Aubrey, do you want to try this?
Oh dear. Sure.
I'm asking, do you want to try it, Aubrey?
All right, let's go for it.
Okay.
Oh, so you want me to say the element? Okay.
Yep. You want a cheat sheet here, Aubrey?
Hold on. I think I got it. Okay.
You want me to give you a big hint? I'm dying to give you a hint, Aubrey.
Is it iron?
Very good. It is iron.
Yes.
Okay, guys. When you have the configuration, when the configuration is written up there and they ask you what element is, aren't these numbers up to the last one, aren't they all going to be the same? It's
Yes.
only the last one that matters. So all you got to do is find where the 3D orbitals are. 4s, then 3D, correct, guys? So I'm dealing with something between scandium and zinc. All I got to do then is count the electrons over. 1, 2, 3, 4, 5, 6. I'm an iron. Blake, did you have a question?
I do not know. Thank you.
Okay. Does that make sense to you all?
It does.
Good, Blake. Guess who's going to do the next one?
Bring it on. All right.
got
So the last full shell is 3D 10.
Not 10, zinc.
10. Oh, wait. Okay. So I know it's got to be on the right by 4. So that would be.
So, Blake, 4p, right? Correct?
Yes. Yeah. So just
All
count
right.
4 over.
Which element begins 2p?
That 2p is a GE.
Nope. 2p.
Oh, 2p. Carbon.
Nope.
2p.
Which one?
2p.
The question I ask is, which element begins the 2p orbitals? Isn't it boron?
Oh, yeah, it is. Yep.
So 3p would be aluminum.
Oh, you go down. I see. And
4p would be what? Starting with what?
Gallium. Is that right?
Gallium. So
Yeah.
you tell
over
me
from that.
what 4p with 4 electrons in it is.
Selenium. Did I say that right? I probably butchered that.
Yep.
Yeah. Selenium. Sorry.
Selenium. Does this seem to make sense? Guys?
Yep.
Make sense?
Yeah.
Okay. Dylan. 4D8. Sorry. What in the hell did I do here? I'm sorry. Hold on a second. I screwed this up somehow. And I don't know what I did. 4s, 5s. There's no 4p14. Okay. Dylan, where are we at?
4D8.
Okay, which element begins the 4D? Which element begins the 4Ds? Just give me the symbol.
V. Or
V.
Y, sorry.
Y. Right. Okay. Count 8 over.
PD. Sure how to say it.
Palladium. Okay. Now, remember I said a few seconds ago that everything up to the final one is going to be the same each and every time. like palladium is going to be the same, or sorry, excuse me, silver is going to be the same up to this point, then I would try and call it 4D9, right, guys?
Yes.
We can cheat a little bit. We can use an abbreviation. And the abbreviations that we like to use is the noble gases are pretty stable. So if I put krypton in brackets, that means that I'm saying the configuration for krypton is up to this point, from 1s2 to 4p6. Each and every time, that configuration is going to be written out longhand like that. If I want to abbreviate it, all I'm going to do is just say, okay, I want to do this easy because I'm lazy. I'm going to say bracket, KR bracket, 5s2, 4d8. I'm sure you guys remember this one because it saves you work. Anybody not know what I'm talking about with the abbreviated version?
I know what you're talking about, but I have a question on it.
Go for it.
Do you include the f orbitals when you're doing the configuration?
Do I include the orbital diagrams?
No, like when you're doing, like say you have that set of numbers on your screen, but you're trying to find TA. Would you include the f orbitals in the
TA? Help me out here. Give me a number. I have no idea what TA
73?
is. I'm sorry?
73.
73. Okay, gotcha. Well, at least I know 72 is hafnium. Go ahead. Yes, exactly, Dylan. You would include,
Okay, all right,
you would go down, that would be xenon in brackets, 6s2, 4f14, then 5d, you have to count this box. Where's this arrow? You have to count this box. So 5d, 1, 2, 3.
Okay, all right, thank you.
These things are kind of funky. The way I learned the periodic table, lanthanide was in here and actinide was in here. So lanthanide would have been a D and actinide would have been a D. The trouble is that different people put periodic tables in different ways. If you count the number of electrons here, it's 15, not 14. So one of them is using this box, whether it's LA or LU. Does that make sense to you guys?
Yeah.
Really and truly. Do you know I'll throw this one out there for a point. How many elements has Schrodinger's equation been solved for?
30?
30? Aubrey, do you have a guess?
No, I do not.
What if I tell you I'll give you a point for the person that comes the closest? Do you have a guess now, Aubrey?
1. I don't know.
Joe, any guesses?
103.
Blake?
15.
And Mian? The guesses? Min, you have any guesses? Aubrey is right.
Oh my gosh, I am. It's 1.
It is 1. The only one that they've solved it for is hydrogen, because hydrogen only has 1 electron. If you add another electron into the mix, you really, really, really futz with those numbers. You futz with them so much that they can't be solved. So hydrogen's the only one that's been, and Schrodinger made this 100 years ago. For 100 years, they still haven't solved helium's Schrodinger equation. Anyway, so where was I going with this? Oh, yeah. So there are some people that would call lanthanide the first 5D. Other people say it's the first 4F. I will not give you one of those examples, okay? I will not give you one of those examples on the test. Are we good with this? We kind of know the abbreviated version?
Yep.
Yep.
All right. Give the name and atomic symbol for the elements that have the following electron configuration. Remember 3p1, Joe. 3p1.
Al, aluminum.
Al. 3d7. Min. What's the element? 3d7. Dylan?
Cobalt.
Cobalt. And 5d6. We're going to go Blake. Blake? Blake's probably eating.
Sorry, muted. Osminium.
Osminium. All right. Now, I want you to provide the abbreviated electron configuration for, we're going to go with antimony, SB. SB is the one you need to remember. Dylan, what's the thing I'm going to be bracketing? What element is going to be in the brackets?
For which element? Sorry.
SB, antimony. 51.
You're going to do krypton.
Krypton. Then where do we go from there? What's the next orbital we put in the sequence?
5s2.
I got to check it. 5s2. Next.
4d10.
And
4p3.
okay, remember, we have to do that tail of the arrow to the head of the arrow. The 5s was before the 4d, but if you look at that chart, you want me to, do I need to bring the chart back, Dylan?
Yes, please.
Okay. End the show. You see it, Dylan?
Yeah.
The last one you said was 4d10. What's the next orbital?
5p.
5p. And we're going for antimony, which is right here. So 5p, how many?
3, but you take one away.
Why
So
do I take one away?
Because you have to fill up the 410.
Fill up the 410?
Or the 4d10, sorry.
No, 4D, the 4D already has 10 in it. I'll get to that in a second, Dylan. I'll get to what you're talking about in a second. But we go krypton, 5s2, 4D has all of its orbitals filled with electrons. So there will be 4d10, 5p3. You good with that, Dylan?
Yeah.
Okay. Slideshow, current slide. All right. What happens if I have an ion? What do you think happens when I have an ion? I have gold plus 3. I want the electron configuration. There's where gold is. Can you tell me? Well, just what would the electron configuration be? Starting with the abbreviated.
It's going to start with xenon.
Did everybody see that? When you're doing the abbreviated, you got to go back to the very start and go up 1 and go over to the noble gases. That's where you're starting, xenon. Okay? Joe.
Yes.
So I'm starting with xenon. What are these two? What are those two going to be?
What are they called, or?
No. What are they? Yeah, what are these two? What are these orbitals going to be called in the electron configuration?
Xenon, whatever it's called.
Now, these two electrons,
S.
what are they going to be in terms of like a 3d10, or what are these two electrons going to?
6s.
6s, how many?
1 and 2.
2.
Oh, yeah.
Okay, now I have gold plus 3. How am I going to deal with gold plus 3? How did gold get to be plus 3?
It lost 3 electrons.
It lost 3 electrons. So if it lost 3 electrons, I'm going to take my gold, 1, 2, 3. So my gold is going to have the same electron configuration as osmium. So that's going to be 6s2, 1, 2, 3, 4, 5, 6, 4d6. Did you catch that? If I was going to go phosphorus minus 3, in that case, phosphorus has gained 3 electrons. So 1, 2, 3, it would have the same electron configuration as argon. 1s2, 2s2, 2p6, 3s2, 3p6. Are we good with that on how to do configurations of ions? Now, Dylan alluded to something not too long ago, in which he said that, oh, by the way, guys, if your electrons are excited, they can appear in any one of the upper levels. It just depends upon the right amount of energy to get it into a particular energy level. All you just have to realize is it's in an excited state. If you take that energy away, it will fall back into its ground state orbital. Okay. I want to do the other thing. Do I want to do the other thing first? No, we're going to do orbital diagrams. We're going to do orbital diagrams first. Now, when you're doing orbital diagrams, you can do it with boxes. Okay? Each box indicates a suborbital. So if I have the 1s, I have one suborbital within the 1s orbital. S's only have one suborbital. 2s also is going to have one suborbital. Now, when I put the electrons in there, I have to put them in so that they don't have the same quantum numbers. If I put them all both in the 1s, the m, the L, and the m sub L are all going to be the same. The only thing that differs them is whether it's spinning in the clockwise direction or counterclockwise direction. So we have to indicate that by putting one of the electrons going up, the other going down. Does that make sense to you?
Yeah.
So each suborbital is going to get 2 electrons. Hund's rule. The lowest energy level is achieved when the number of electrons with the same spin is maximized. In other words, you want to fill all of the suborbitals with the electrons spinning in the same direction. You want to put the arrows all going up when you put them into the suborbitals. It is only when you have filled all the individual suborbitals and you have to put a second electron in that you put it in the opposite spin. Does that make sense, guys?
Yeah.
3 rules with Hund's rule. Electrons fill starting with the lowest n and moving upwards. In other words, you fill the orbitals that have the least amount of energy in them first. No 2 electrons can fill one suborbital with the same spin. That has to do with Pauli's rule on no 2 electrons having the same energy. If you have degenerate orbitals, the electrons fill each orbital singly before any electron gets a second electron, and they all fill with the spins going in the same direction. So if I'm doing orbital diagrams and I'm just drawing lines like this, if I have lithium, I have 3 electrons. The first 2 electrons go in my 1s. The first electron goes up. The second one goes down. There's no more degenerative orbitals in the 1s. I have a 3rd electron. It goes in the next energy level above 1s, which is the 2s. And it gets in there with a spin. Conventionally, we mark them with the arrows going up. Is there anything to say that the arrow's going up? Does it have to be going up? No. It could just as easily have been going down, because the only thing that influences the energy of that electron is if it's in a magnetic field. Now I deal with beryllium. I have to put 1 more electron in. I have 1 more space in the 2s, but I have to put it with the spin in the opposite direction because of Pauli's rule. I go up to boron. I have another energy level, only these are the 2p's. The 2p's have 3 degenerative suborbitals. In other words, the energy of the 2px, the 2py, and the 2pz are all the same. I could put that electron in any one of the 3 of them. Conventionally, I want you to put it in the one to the far left. Conventionally, I want you to put it with the spin up.
So would the M's of L for the lithium be?
There are be 0.
0?
Yes.
Okay, all right, thank you.
Remember, Dylan, M sub L's can only be plus L to 0 to minus L, right?
Okay.
L is equal to 0 for S orbitals, right?
Yeah.
So M sub L can only be 0. All right. Now I've got boron. I'm going up to carbon is my next one. Okay. Now, how many different ways can I put carbon in there? I can put it 1 electron in each suborbital going in the same direction. I can put them both in one of the suborbitals but with different spins, or I can put them in separate suborbitals, but one spin going up, one spin going down. The energy level that is the stablest, the least amount of energy, is this state. You fill the electrons in there with the same spin. You put one in each. As you are adding electrons, you fill empty orbitals first. So I'm not going to do this because I've got empty orbitals here. I am going to put the spin in the same direction so that I have one electron in the 2px, one in the 2py. Both of them are going up. I go to nitrogen. How is nitrogen's orbital diagram going to look? Blake, where's the next electron go?
For nitrogen?
For nitrogen.
Let me pull up that periodic table here.
Don't look at that. Look at this. Look at what's on the screen, Blake.
Okay.
What's on the screen right now is carbon. What I'm asking you is nitrogen has one more electron.
Oh, if it has one more,
one more electron in the orbital diagram. Where's it going? And is it going to be spinning up or down?
it'll spin up with 2pz.
2pz. When you go to fill the D's and the F's, same thing happens. Only in the case of the D's, instead of 3 suborbitals, I'm going to have 5. And I have to fill each orbital with 1 electron. So I have to fill 5 electrons with the spin going up. Before that 6th electron, I have to put it in the same orbital as one of the other electrons.
What are the subscripts for the d orbitals?
What are they? I believe x squared, y squared, z squared, and x squared minus Dylan, I'll look it up for you. I'm not gonna trust my memory on that.
Okay.
So again, nitrogen, all 3 of them are going up. Oxygen, I have another electron. It has to pair up with one of the electrons in a suborbital, but it spins going down. Fluorine, 2 of my electrons are spinning, are being put in the same orbital. Only 1 has a free electron. Neon, everything is filled up. Are we going good with this, guys?
Yeah.
Okay. I got 2 more important things. Okay. This is a minor thing. This is just what I was talking about before. As you get more electrons in an orbital, there's more repulsion, which makes it a higher energy. That's why the 3D is above the 4s. Okay, if I'm doing arsenic, I've got my 1s, 2s, 2p's, filled out, 3s, 3p's, stop that. 4s, I fill up the 3d, and then arsenic has 3p's in it, 3 electrons in the 4p orbital, so they get put in all with the same spin. I'm dealing with this aminal. Which element am I dealing with?
Krypton?
Nope. Krypton's a noble gas. Krypton would have everything filled here.
So then bromine.
Bromine. What Dylan did was he looked at the 4p, where the 4p's were in the periodic table, and he counted 5 electrons over there, and you found out it was bromine. Okay, 6p, 2 electrons. And I've forgotten what it is.
Would it be barium?
No, it's not barium. Barium is in the S's, would end in an S. Barium is 6s2. I'm looking for the 6p2. Come on, guys.
Lead.
Lead. Lead is right. Now is when we get into what Dylan was alluded to. It is energetically favored to have a half orbital filled. So if I look at chromium, the normal configuration for chromium should be 4s2, 3d4. But half-filled orbitals have energetic stability. Remember, the 3d is very close in energy to the 4s. So if we promote one of the electrons from the 4s, we have a half-filled 3d orbital, which then makes it energetically the same as the 4s. So energetically, 4s1, 3d5 is favored over 4s2, 3d4. Are we good with that, guys? Do we understand that? We want to look for half-filled and full-filled orbitals. There are going to be 2 areas that we need to be concerned about. Chromium, molybdenum, and tungsten. All of these normally would have a D4 electrons. If I add one more electron to that, that would make a half shell. So one of the 4s's gets promoted to make that D shell be half filled. So molybdenum's end couple of configurations would be 5s1, 4d5. Tungstens would be 6s1, 4f14, 5d5. The other area you need to be concerned about: copper, silver, and gold, because these have 9 electrons in the d orbital. If you add one more electron, you fill the d orbital. So copper's configuration is going to be 4s1, 3d10. Silver's 5s1, 4d10, and gold's is going to be 6s1, 4f14, 5d10. Are we good with that? Only 2 areas we have to worry about. Yes. Does it occur for the F's? Yes. Don't worry about the F's for me. Just know that it can occur in the F's. Copper down, chromium down. These are just explaining what I just went through. Okay, I have to get through the quantum numbers before I'm willing to stay afterwards, but I have to get through the quantum numbers before before we end tonight, okay? All right, conventionally, which means I do it this way, so you're going to do it this way. N can be an integer up to 7, determined by where it is in the periodic table. L can be up to n minus 1, again, determined by where it is in the periodic table. Now, if you have suborbitals, which means P, D, and F, then you have different M sub L levels. The M sub L's, I want you to label from left to right, from minus L through 0 to plus L, in that order. So that if I have the P's, my orbitals are going to be minus 1, 0, plus 1. D's, minus 2, minus 1, 0, plus 1, plus 2. My M sub S's can be plus a half or minus a half. The first electron going into a suborbital gets the plus 1/2. The second electron going into that same orbital gets the minus 1/2. Do you understand the rules by which I am having you obey this? Is there any confusion? If you're confused, tell me now, because this will be on the test on Tuesday. All right. Again, barring any outside influence, there is, if you're putting one electron in the M sub L suborbitals, there's really no difference. Or there's no difference that the M sub S has to go in with the spin going in the up direction. We're just doing this for convention's sake. Okay. Last electron added for sulfur. I want the 4 quantum numbers for the last electron added for sulfur. The best way to do this, draw the orbital diagram. If I draw the orbital diagram, I'm left with 4 electrons in the 3p. As the electrons get added to the 3p, remember, we're going from left to right. This one is minus 1. This one's 0. This one is a plus 1. So they get added up, 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 then down. First thing, guys, they're being added to the 3p. Immediately, I know what n is. Aubrey, what's n? 3p. 3p.
3.
A number between 2 and 4p.
1, 2.
A number between 2 and 4 is 2?
Yeah.
Okay, you want to go with that. Remember, when we're doing the configurations, remember, we said the number in front of the letter was the shell it was from. It's the n number. So if I'm telling you it's in 3p, then n has to be 3. Now,
I said 3 first. You made me guess myself.
You're going to argue me on this, aren't you? All right. Now, second quantum number is L. If you remember back to Tuesday's lecture, and I gave it when I was doing the review, this first thing this time. If an L value is 0, that is S. If an L value is 1, that is P. 2, it's D. 3, it's F. So if I am dictating that this is in the 3p level, then the P indicates that my L number is 1. So if it's 3p, my N is 3, My L is 1. Now we got to figure out where that last electron went in for the M sub L. Remember, just by my convention, -1, 0, -1, 0, +1. Up, up, up. Last one went in to which orbital?
-1.
-1. So that is what my M sub L is. Blake, is the arrow up or down? Is there already an electron in that suborbital?
Yes, the pair is complete.
So first electron is a +1/2 in the suborbital. The second electron is
The negative.
negative. So my 4 numbers for this are 3, 1, -1, -1/2. I've only drawn out the last couple of orbitals in the for cobalt here. Joe.
Yeah.
3Ds are where I put the electrons in last when I did my orbital diagram. I had 7 electrons that had to go into 3D. They go up, 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 up. Then I have to add them to already half-filled electrons, half-filled suborbitals. So I get a down one and a down one. Again, we are marking the orbitals as -2, -1, 0, +1, +2. This is the last electron that went in. So Joe, what is my N?
3,
My L?
2.
Because we're in the D electrons.
Yes.
Okay. Now we're dealing with my M sub L. -2, -1, 0, +1, +2. Where was the electron added last?
-1.
-1. First or second electron in that suborbital?
Second, so it's -1/2.
Okay, so we have 3, 2, -1, -1/2. Going back the other way. All right. If we're going back the other way, we got to look at and interpret the quantum numbers. 4, principal quantum number. That indicates the shell it's in. Okay. 2, that indicates the L, the orbital shape. 2 stands for F, S, P, or D?
D.
D. So I'm in the 4D. How many suborbitals are there in the 4D?
5.
5. 1, 2, 3, 4, 5. Okay. Now I've got my 5 orbitals drawn down. Again, I'm marking them from left to right. -2, -1, 0, +1, +2. All right. Now, at this point, guys, look at the molecular spin. Is this the first or is this the second electron in the suborbital?
Would it be the first?
It's the first. Okay, and Blake? I'm entering the electrons in from left to right, correct?
Yes,
So does one go into -2?
it does.
Does one go into -1?
Yes.
All right, so I'm at 4D and there's 2 electrons in it. You have a periodic table near you, Blake?
I do.
What is that element?
4D
Yes.
plus 2, would it be 10?
Nope.
Maybe I'm getting this wrong. 4D.
10 is over in the P's, Blake.
So D's in the middle.
These are in the middle.
Okay, so
You're on the
plus
right
2.
level, though.
Zirconium.
Zirconium. Okay. Again, the way I did this, I'll go through the slides. Okay. I know it's in the 4th shell. I know the 2 dictates it's the d orbital, so I draw them out. Guys, I'm lazy. I don't like to draw boxes. I just draw lines. Okay. Next thing I'm going to do is I'm going to realize that the spin was a plus 1/2. So I know it's the first in the suborbitals. I know that the last one in is a -1. So starting from the left over, one goes here, one goes there. That means I only have 2 electrons in the 4D level. That tells me that I have zirconium. Okay, guys, I have used up my time. And I think somebody dropped out anyway. I think Amber dropped out for whatever reason, okay? Are we good with these or do you need more practice with them?
That should be good.
Joe, Dylan, Min?
I think I'm good.
Okay. Joe?
Yeah, yeah.
Joe, I'm here. Joe, Min, I'm here. Guys, I'm here. I'm willing to stay over.
The first one you made me do, I had no who I was doing, but then it kind of helped, so I actually understood. First,
okay.
1S2, 2S2, no clue, but then I got it.
Try and work through these because, as you can see, I give you I go one way and then I go the other.
Yeah, I think this is more simple. Yeah.
Okay. Test on Tuesday up to this point. Any questions, ladies and gentlemen, or gentlemen at this point?
So will we not have effective nuclear charges on it?
No.
Okay. All right. Thank
Dylan,
you.
Dylan, I haven't written the test yet, so it will not be on there. Anything else, guys?
Nope.
Mm-mm.
Yeah, and let's hope I don't do the same mistake I just did because my morning lecture, I didn't stop the recording for 3 hours after it.
Oh, no kidding.
No kidding. It's okay. I know how to edit it now.
There you go.
Okay, if that's all, ladies and or if that's all, gentlemen, then I go to your, Blake. I know you're hungry. Go get your dinner. I'm having
Thank you,
steak
sir.
tonight. I'm having
I'm
filet.
jealous. Nice.
Yeah, with French fries. How I talked my wife into that one, I don't know.
Hey man, it's either that or potato or mashed potatoes. So.
Oh no.
Got one of the two there. Do you like yours with horseradish or do you like grilled
no,
onions?
Actually, I like if I'm gonna go for something, I'd rather have a Alpov or a Bernays.
Wow, fancy with it. Nice.
So, if I'm gonna do something.
Yeah, I mean, if you do it right?
My wife does something where she has a Zinfandel wine, and she uses the Zinfandel wine, balsamic vinegar, and peppercorns.
Ooh.
And she literally takes like 2 cups of the wine, reduces it down to like a quarter cup, and that stuff is rich and it tastes wonderful.
You're making me hungry.
I'm sorry.
All right,
Anyway,
we'll appreciate it.
Take care, guys. I probably won't talk to you on Tuesday, but we'll get through it.
We'll try.
We're about 3/4 of the, hey, look at it this way. How many quizzes are there?
We only have 2 left.
3.
I was going to say 4.
Well, actually, sorry, Dylan. Technically speaking, there are 5 left. 5? You just did 15, right?
Yeah.
Yeah.
So you've got 5 left. 4 scheduled and 1 pop. So I literally did this on purpose. I busted your butts with quizzes in the first half of the semester so that it would kind of ease down as we were going along.
Cool.
So, plus it's harder for me to ask questions on this stuff.
I had sent you an email about the lab for Tuesday.
Lab for Tuesday. Help me out here. I don't normally do the labs until I do that Tuesday's lab prepare for that on Monday. Give me what's the subject matter? It's the one after, is it chromatography, Dylan?
Spectrophotometric determination of a food dye.
Oh, you're talking about the one that's due.
Yes.
Okay, I'm sorry. Go ahead, ask your questions.
So I calculated my equation of line of best fit, but I got in the 200,000s.
I did too. Like 223, right?
All right, did you do Excel or did you do it by hand?
I've used Excel.
Okay.
So that'll be okay.
Yep.
All right. I just felt like it was a huge number and I felt like it was wrong.
Nope. I think if I'm not mistaken, I even warned you that it was going to be up around five decimal points to the left of. It was going to be 10,000 or more. I thought it was going to be around 10,000.
Yeah, I was expecting a much lower number after listening to the lab. So that kind of threw me off. I went with it because I redid the math and it was right. So
I'm trying to look to see if they included a graph.
Should our graph should it had 4 points or 5 points?
Should have 4.
Okay, good.
4.
I didn't know if we wanted
1, 5, 10, and 15.
Okay, cool.
The dilutions, cool. 1, 5, 10, and 15. Those
I didn't know.
I'll shut up.
I didn't know. No, I'm sorry, man. I didn't know if we wanted to also include the unknown sample.
No, because you don't know what the concentration of the unknown is.
Oh.
What you're doing is you did the graph, you got the slope, right?
Mm-hmm.
So the Beer's law equation is the absorbance is equal to the molar absorptivity times the concentration, right?
Mm-hmm.
So when you did the slope, Blake, that was what the molar absorptivity was. So if you divide your unknown absorbance by your slope, you get the concentration of your diluted Gatorade sample.
Okay. I was just going through it and I was thinking there was a way I could double check it off the unknown sample because it's the same dye and it would have the same absorbance somewhere on that graph. But I just didn't make the connection.
Okay. All right. Do you have your graph with you, Blake?
Yeah, I could quickly pull it up. Okay, I got it.
All right. Now, do you know what the absorbance of your unknown was?
It was 2.5.
Okay. Go up on the y-axis 2.5. 2.5 or 0.25?
2.5.
No.
That's for the stock unknown solution.
It's the other number. Thank you, Dylan.
Yeah, the diluted.
Exactly. Yeah, I thought we were going to do the unknown stock solution on the graph somewhere.
No.
Oh, okay.
Blake, what happened? Why he did that? Why the guy wrote it this way and why Dr. Musgrave included that number is beyond me because it only serves to confuse you. Okay.
Mm-hmm.
You can't use absorbances above 1. They're not reliable because it's the same thing. Absorbances are an exponential. It's kind of like earthquakes. All right. You know how they say that Earthquake with a 2 Richter scale is 1/10 of one with 3.
Okay.
Does that make sense to you, Blake?
Yes, exponential.
So literally, when you go above 1, the numbers get real itsy bitsy and you can't really tell one from the other, and it's exceedingly unreliable.
Okay.
So what you want to do is, if your solution is above 1, you want to dilute your solution to a level where you get it somewhere between 0 and 1. That
sounds familiar.
That's why the solution got diluted.
Okay.
And you're using the bottom number. Dylan, do you remember what number that was?
0.28.
Okay. Now, Blake,
Mm-hmm.
I want you to go up the y-axis to 0.28. Okay?
Gotcha.
Then I want you to go straight over until it meets that straight line. Okay?
Okay.
Then take it straight down.
So I'm at like really small number, 0.0000001213.
Okay? Is that close to your calculated value?
Yeah, it is because I'm using it off the graph. So
Well,
I see it. I was trying to correlate something that shouldn't have been in this graph. So that cleared it up for me. So appreciate it.
Good.
I thought there was a way to double check your answer because I'm like, if it's on a graph, but yeah, I was just using the wrong value. So that totally makes
Blake,
sense.
there is. It's exactly what I told you to do.
Yes. Yep. Exactly. Not the 2.5.
Not
so
the 2.5.
0.28. Yep. Exactly. So cool.
Okay. I wonder how many people are going to get that wrong now.
It was going to be me.
Literally speaking, if you look at the PowerPoint, did I not put it in the PowerPoint?
You had to, you said it out loud. I had to look over the YouTube video.
Oh.
Me too. I watched it like 3 times.
It's this lab is simple. The lab really is simple. The calculations are very, very simple.
The
problem is you're not getting that lecture in front of it or the lecture behind it to reinforce you. It's just something that's out of the blue that's thrown in here.
Completely agree. Very simple math. I felt unconfident doing the whole thing, but the math didn't lie, so I just went with it. So
again, go back, put the 0.28 in there, and solve it that way, and you'll be good.
Cool. Yeah, I think my points are fine. I just didn't know if there should be a 5th one for the unknown.
No.
So cool.
I have one last question.
I'm here, Dylan.
For the standard enthalpies of formation, will you give us that, or should we print off a copy?
I'll give you those.
Okay. All right. Thank you.
I will give it. It's not going to be like the Pearson homework where you got to find the textbook or look it up online.
That's exactly what I did.
Enthalpies will be directly under the question.
Okay. All right. Thank you.
No problem.
Have a good week.
Blake, if it's all the same to you, I'm going to go eat my steak now.
Enjoy, sir.
Take care.
Have a good one.
All right. Bye.
Bye.